Chemistry Connections in Depth by Kate. The topic we're talking about today is climate change and the problems and all the different components of it. First, we'll talk about the chemical compounds or bonds within greenhouse gases, which is an essential cause of climate change, as greenhouse gases such as CO2, nitrous oxide, and methane end up warming up our atmosphere and trapping heat inside, which causes the Earth to warm up. Chemical compounds are when atoms of different elements are joined and held together by different types of bonds. There are many examples, but the most common are ionic bonds, when a compound is bonded together due to one element, the metal, losing valence electrons, and the other element, the nonmetal, gaining the valence electrons lost. An example shown in the diagram to the left is sodium chloride, where sodium loses one valence electron and chlorine gains one valence electron in order to fill a shell of 8 valence electrons total and make the compound stable. As a result, the positive ion of sodium and the negative ion of chlorine are attracted to each other, and they form a compound that is bonded using ionic bonds. Covalent bonds are different. They happen when nonmetals react with each other in order to form compounds. They share a pair of electrons between elements in order to reach a stable shell of valence electrons, as nonmetals usually have a higher amount of valence electrons in their shell. They can't just give up all of those valence electrons. One example is H2O, where both hydrogen and oxygen are nonmetals. This is also another word for water. As you can see in the diagram to the left, the single lines represent covalent bonds. Now, each of those bonds is a pair of electrons. So each hydrogen atom has one valence electron, and the one oxygen atom has 6 valence electrons. Now, one electron from oxygen is shared with one electron from hydrogen in order to form a pair of electrons, which is then shared between both of them. So now oxygen has a stable shell of 8 electrons, and hydrogen has a stable shell of 2 electrons. Now, relating this to climate change, carbon dioxide is one of the most abundant greenhouse gases. It is a covalently bonded chemical compound, as both carbon and oxygen are nonmetals. There are 2 pairs of electrons shared with each oxygen atom, giving each oxygen atom 8 valence electrons. You can see in the diagram here that the oxygen has 6 electrons and the carbon has 4 electrons, but there are double bonds between the carbon and oxygen atoms. So the carbon now has a full shell of 8 electrons, and the oxygen also has a full shell of 8 electrons due to the double bonds. Nitrous oxide is another example. It is a powerful greenhouse gas, and it comes from activities such as agriculture and fuel combustion. It is a covalently bonded chemical compound, but it has different resonance structures. This means that atoms could be rearranged in different ways. For example, if you look at the diagram, the Lewis dot diagram pictured on the left, the triple bond between the 2 nitrogens could be flipped over, and the nitrogen could be on the right side, and the oxygen could be on the left side, rather than the nitrogen being on the left side and the oxygen on the right side. And this would still allow the compound to be stable, which means that there are different resonance structures. Next, we are going to talk about methane and organic compounds. Organic compounds are created because carbon atoms have 4 valence electrons, so they typically share them with other atoms using covalent bonds, as it would be too hard to either gain 4 electrons or lose all 4 of its electrons. Now, each carbon atom needs 4 bonds in order to achieve stability. Hydrocarbons are the simplest organic compounds that consist of combinations of carbon and hydrogen atoms. The carbon atoms are typically in a chain with hydrogen atoms attached to the sides. Single bonded hydrocarbons are called alkanes, and for the number of carbon atoms in a chain, there is a prefix. For example, propane means there are 3 carbon atoms. The suffix also relates to the number of bonds between the carbon atoms. So ane means that all the carbon atoms are single bonded. Methane is a powerful greenhouse gas. It is more powerful than CO2 by 80 times, and it is released into the atmosphere from industrial sources, landfills, coal mining, natural gas systems, and agriculture. All of these compounds that I've mentioned serve to increase the amount of greenhouse gases in the atmosphere, and they end up trapping more heat on Earth, and they speed up global warming. Methane is the simplest organic compound consisting of carbon covalently bonded to 4 hydrogen atoms. As you can see, carbon is currently sharing each of its 4 valence electrons with 1 hydrogen atom, so that the covalent bond gives carbons 8 valence electrons in total, and each hydrogen has 2 valence electrons. The name methane comes from its status as an organic compound, and as you can see, the name methane does not have the words carbon or hydrogen in it. Instead, it has the prefix and suffix given to organic compounds. In addition, organic compounds also consist of natural gas, and when we move on to burning fossil fuels, the fossil fuels that we are burning in order to release carbon dioxide into the atmosphere come from organic chemistry and organic compounds. Now we're moving on to the chemical reaction of burning fossil fuels. Chemical reactions are the reactions between 2 or more elements. This equation below describes the reaction between magnesium and oxygen in order to form magnesium oxide. You can see it's 2Mg plus O2 equals 2MgO. And you can see that it's a reactant plus a reactant, and it turns, we don't have the arrow sign, but so use an equal sign, but it turns into a product. That is the way that chemical equations are formatted. Now, there are different types of chemical reactions. There is synthesis, there is decomposition, but some of the most simple ones are endothermic reactions and exothermic reactions. As you can see on the diagram, endothermic reactions require heat from their surroundings. There are different arrows pointing into the chemical reaction, and this heat is required in order to perform the reaction. An example equation would be reactant plus heat turns into the product. Photosynthesis is an example of this, as it requires heat from the sun in order to perform photosynthesis and get glucose from the carbon dioxide. Now, because it requires heat from its surroundings, it is usually characterized by a temperature drop, and the air or the surroundings usually become colder. Exothermic reactions are the exact opposite. They produce heat as a result of the reaction. An example equation would be a reactant plus a reactant turns into a product plus a heat. As you can see in the diagram on the left, heat comes out of chemical reaction, and as a result, the surroundings usually become hotter. So exothermic reactions are characterized by an increase in temperature rather than a decrease. An example of this is like setting a candle on fire, or that is a combustion reaction, which is a type of exothermic reaction. Now, relating this to burning fossil fuels, which is the main cause of greenhouse gases being released into the atmosphere in the first place, the chemical reaction for this would be fossil fuels plus oxygen turns into CO2 plus water. As we don't know the exact amount or type of fossil fuels, as they can be so many types of organic compounds and of oils and natural gas, we can't write a single chemical equation to predict the amount of carbon dioxide produced from burning fossil fuels. Overall, this chemical reaction is a combustion reaction. As you can see, when you burn fossil fuels, heat and energy is being released. We use this to make electricity, power our cars, for lots of uses, and this process releases energy and heat. But also, in the first place, energy is needed for fossil fuels and oxygen to react. So it is also an endothermic reaction, because in order for the reaction to happen, fossil fuels and oxygen need to come into contact with heat for it to produce carbon dioxide and water, which is really a byproduct of the energy that we get from burning fossil fuels. But as you can see, the reaction of burning fossil fuels releases CO2, which is a greenhouse gas that is that contributes greatly to the greenhouse gas effect and warms the planet. And those are only some aspects of the chemistry of climate change. I'm sure there is much more, but thanks for listening to my presentation.